They were too trivial.
The solution to question 4 from the homework, um,
I
the
apologize for question 4. Yeah.
the kth or the term k had all of these derivatives up to k. Is that equivalent to some sort of state transition matrix? Um,
Let me just understand. Problem 4 is the one that's called Jordan normal form, the one that has a weird matrix, raising or lowering operator matrix. That's the one we are talking about.
yeah, and it accumulates these time derivatives along the upper uh,
Yeah.
triangular.
I feel very bad about this problem because this problem is the answer to a totally honest question that all of you should always ask, which is, you know, often we are told, especially in physics, that we are supposed to look at eigenvalues of a matrix and its eigenvectors. Now, the honest question is this always possible? So it turns out that no. So since 19th century, we know it's not possible because it's, from a mathematical point of view, it's perfectly okay to have subspaces which have only one eigenvector, even though they're high dimensional spaces. So the eigenvectors don't span the space. Now, what's my problem? In quantum mechanics, you never see this. In mechanical engineering, you never see it. And honestly, it's an answer to mathematical question that everybody teaches as a linear algebra, but I can't think of a simple example where we actually use it. So I feel guilty about this problem. So it's just a math problem, but basically you're right. You know, when you look, what happens is when you have these nilpotent things, you have to take care of number of derivatives of the function, not just the first one. But you know,
When when you're trying to make an algorithm that detumbles a satellite using what are called magnetorquers, um,
yeah,
it's essentially pulsing current through uh, coils of copper based on what you think your rotation is and uh, I guess the magnetic field of the Earth.
hmm
That is very, it's very uncommon for that to not be degenerate. And I don't think it has been used in this uh, case, but I do think it would be justified in being used there.
yeah. So uh, as I mentioned before, when you do this kind of problem, like simplest version of the problem you're mentioning, in celestial mechanics, there are Lagrange points, which are the points in which the gravity of three bodies balances exactly. So if you stand there, you don't move because the three bodies attractive is the same strength. So that's called Lagrange point. And Lagrange point has to move with the system because everybody's moving, right? So now Lagrange point always has a number of degenerate eigenmodes. And these are these eigenmodes of continuous translations, which you can use to go from Earth to Lagrange point. And there's a bunch of them. They're
Yeah.
exactly degenerate. They're precisely degenerate. They're not approximately degenerate. And that's a consequence of symmetry. Now, once you're there and you've fixed all these guys, you're in the center of mass frame and in some rotating frame, etc., the rest is not degenerate unless there is another principle at work, and usually there isn't. So usually, you run out of symmetries and the rest is real calculation. So that's not the problem. This problem is a problem in which you do have degeneracy, but you don't have a Jordan form because you can actually exactly, every time you have this continuous degeneracies, you can diagonalize them and find eigenvectors for them, etc. So now, numerically, it can happen that you have near degeneracies. And then, numerically, the hell breaks loose and you have to figure it out. And then Jordan forms help you. Understanding that you could approximate near degeneracies by this stupid matrix. And if you give me an example where that happens, I will include it in my notes, but I just can't find it.
Yeah, I'll
So
follow
it's one of
up.
those things that it's elementary math, because when you look at 2x2 matrices I gave you in notes, you have to think of that case. The problem is in physics, I never see it. And, most of my colleagues look at me blankly. What is a Jordan form? So I don't think this is an example of that, but, I might be wrong.
I hope to prove it.
What? Yeah, I
I'll
mean, please show me. I'll
yeah.
be, grateful, because I feel guilty teaching you useless math, but I can't teach you something that doesn't work for 2x2 matrix, because 2x2 matrix has 3 possible cases. Either eigenvalues are different. Now, in a world of data, there's some random numbers that you measure, different pictures of faces, and all eigenvalues are always different. In the world of science, when you have exact symmetry, that forces some eigenvalues to be the same. Exact symmetry puts eigenvalues in multiplets. Good. As you'll discover later in the course, it has to do with some compactness, something, and they're always diagonalizable and not Jordan form. They're always subgroup of unitary group, all these translations, as we'll see later. Fine. So that's what everybody knows. But anyway, so I feel bad about problem number 4. But, I can sneak it in because people who know quantum mechanics know they're raising and lowering operations. But I'm really cheating. It's not the essence of it.